Welcome to our solution series on UPSC 2019. Today we are going to take the topic of linear algebra. This is question number 1C. It says let T, where it ranges from r square to r square, be a linear map such that T2, 1 is equal to 5 by 5, 7 and T1, 2 is 3, 3. So if A is the matrix corresponding to T with respect to standard basis E1 and E2, then we have to find the rank of matrix A. Such kind of questions are invariably appearing every year. So we will start our solution. We can write this AB belongs to alpha V1 plus beta V2, where A, B, alpha, beta belongs to R. So here I have taken V1 as 2, 1 and V2 1, 2. So these are vector spaces. So I can write this as AB is equal to alpha. In case of V1 we will write 2, 1 plus beta 1, 2. So from this we can find our two linear equation. A is equal to 2 alpha plus beta and B is equal to alpha plus 2 beta. If we solve these two equations, if we call this as equation 1 and 2, we can multiply equation 2 by 2 and subtract it from equation 1. So this becomes 2 alpha plus 4 beta is equal to 2b, and this becomes 2 alpha plus beta is equal to a. So this one get cancelled, so we will get 3 beta is equal to 2b minus a. So we get our beta is equal to 2b minus a divided by 3. So we can put this value in any equation and get our answer for alpha. So we will write b is equal to alpha plus 2 beta. So this gives 2b minus a divided by 3. Alpha plus 2 times of. So if we are going to solve this equation, we will get alpha is equal to 2a minus b divided by 3. So we have got the value of alpha and beta. We'll put in this. So we can write our AB is equal to alpha is 2a minus b divided by 3 into 2, 1 plus 2b minus a divided by 3, 1, 2. So we have given the standard basis with respect to that. So we can write this. First we will take the transform. So we can write this as t and here t. So now we can put our values for standard with t 1, 0. So this gives me 2 by 3 and transform of 2, 1 is 5 by 7 plus here b is 0. So this gives me 1 by 3. T 1, 2 is 3 by 3. Similarly we can write for t 0, 1. So here we can write this as minus 1 by 3 and this gives 5 by 7, and here a is 0, b is 1. So I will write this 2 by 3, 5, 7. So we have got the transformation over here. So we will simply put the values. So we have got T10 as, if we compute this, 14 minus 3, that is 11 by 3. This is, sorry, 10 minus 3 is 7, and 14 minus 3 is 11 by 3. Similarly, we will find for T0, 1. This will gives me minus 5 plus, here the value is 3 by 2, 3, 3. So minus 5 plus 6, this is 1 by 3. Minus 7 plus 6 gives minus 1 by 3. So we can write this, our matrices, as transpose of this one, 7 by 3, 11 by 3, 1 by 3, this 1 by 3 transpose. So we can write this as 7 by 3, 1 by 3. There is a slight mistake over here. So this can be written as 7 by 3, 11 by 3, 1 by 3 minus 1 by 3 transpose. So this gives 7 by 3, 11 by 3, 1 by 3 minus 1 by 3. So if we compute determinant, this gives me minus 7 and minus 11 divided by 3. So this gives me minus 18 by 3. So this gives minus 6. So this is not equal to 0. So from here we can get our rank as 2. Now I will take the next question. This is question number 1D. If A is equal to 1, 2, 1, 1, minus 4, 1, 3, 0, minus 3. This is 3 cross 3 matrix. And similarly B is also 3 cross 3 matrix, where we have given the value of B 2, 1, 1, 1 minus 1, 0, 2, 1, minus 1. And we have to show that AB, that is multiplication, is equal to 6 of I3, that is identity matrix, which is of the order 3 cross 3. And using this result, we have to solve this equation. 2x plus y plus z is equal to 5, x minus y is equal to 0, 2x plus y minus z is equal to 1. This is asked for 10 marks. This is the easiest question that one could have asked for. We have to use first, show our matrix multiplication. So we will multiply A and B. This is 1, 1, 3, 2 minus 4, 0, 1, 1 minus 3, and this is 2, 1, 1, 1 minus 1, 0, 2, 1 minus 1. So this is 3 cross 3, 3 cross 3. So this should be, if M cross N and N cross P, so this and this should be the same for matrix multiplication. So here we can see 3 and 3, they are same over here. So we can write this 1 into 2 plus 2 into 1, 2 plus 1 into 2. Similarly, we will 1 into 1, 1, 2 into minus 1 is minus 2, and 1 into 1 is plus 1. 1 into 1 is 1, 2 into 0 is 0, 1 into minus 1, minus 1. Similarly, we will compute for other parts also. This is 1 into 2, 2, minus 4, then plus 2. Here 1 into 1, minus 4, minus 1, plus 4, plus 1. Here 1, this is 0, and 1 into minus 1 is minus 1. 3 into 2, 6, 0, minus 6. Again 3 into 1 is 3, plus 0, minus 3. 3 into 1 is 1, 3, 0 into 0, minus 3, plus minus 1, plus 3. So we get our answer as, if you take 6 outside, so this is 1 0 0 0 1 0 0 0 1. So we can say this is equal to 6 times I3. Okay, so we have proved the first part. Now using this result we have to solve this equation. The result is AB is equal to 6I3, and we will write this equation in matrix form. 2 1 1 1 minus 1 0, and this is 1 minus 1, this is 2 1 and minus 1 into x y z is equal to 5 0 1. Alright, so we can see here this is B and this is capital X, and I can take this as say C. So I have to use this result. So I have to find this X. So this is B inverse C. If we take B inverse on both sides, so this will be the identity matrix. So we have got our X as B inverse C, but we have to use this result as well. So if I take again B and B inverse, so I can write this as A B inverse is equal to 6 B inverse. So B inverse is equal to 1 by 6 A. So I can write capital X is equal to 1 by 6. How much? B inverse is 1 by 6 A. So we have to just multiply A and C. So this gives 1 by 6 multiply 1 2 1 1 minus 4 1 3 0 minus 3, and this is my 5 0 1. Okay, so I will write here the whole thing and I will get the values. So I get X is equal to 1 by 6. See, this is 3 cross 3 and this is 3 cross 1. So what will be the order? 3 cross 1. Okay, so we will get it. How much? 3 cross 1. 1 into 5 plus 0 plus 1 6. 1 into 5 0 1 6. 5 into 3 15 0 0. 15 minus 3 is 12. So we get our answer as 1 1 and 2. If you put this value, you can cross check, but we have to use this result. That is the most important. So here matrix inversion, inverse of a matrix is important. Matrix multiplication is important. So this is a basic question that one could have expected of. Now I will move to the next question. This is question number 2b. Let A and B are two orthogonal matrices of same order and det A plus det B is equal to 0. That is determinant A plus determinant B is equal to 0. Then we have to show that A plus B is a singular matrix. This question was asked for 15 marks. And now UPSC is oftentimes asking in linear algebra theorems or some properties of orthogonal matrix, Hermitian matrix. Last year also they have asked. Now if we understand the basic properties, then we will be able to solve this question. What do we understand when we say a matrix is orthogonal? Suppose A is orthogonal, that means A into A transpose is equal to I. Similarly, B is also, and it is of same order. And we have given that determinant A is equal to minus of determinant B. Okay. So if I write A determinant A and determinant B, then its product will be opposite. Why? Because if we take plus, then it is going to be minus. If we take minus, then it will be plus for orthogonal matrices. Now we know this property that det AB is equal to det A into det B. So we can write this as det AB. This is a point number 1, equation 1, equation 2. And we have to prove that A plus B is a singular matrix. That means if we are able to show that determinant of A plus B is equal to 0, then our work is done. So I will write A plus B is equal to AI plus BI. This can be written as A into B to B transpose plus B, and in place of here I can write A transpose. Now I will take A common. I can write this as B transpose plus A transpose, and whole B I will take common. Okay. Now I will take determinant, that is A plus B. So this can be written as determinant of A into determinant of B transpose plus A transpose into determinant of B. Now we have written like this. Now I am going to use this one. Determinant A, determinant B, I will write as determinant A, determinant B. So I will write this as determinant of AB. Okay, and I can write this as determinant of B plus A whole transpose. And we also know this property that no matter if we take the transpose, its determinant is the same. So we will exploit this property and we will write this as determinant AB, and we can write simply A plus B. Now we know this value, determinant AB is equal to minus 1 for this orthogonal matrix. So this gives me minus determinant of A plus B. This is determinant A plus B. So what result we are getting? We are getting determinant A plus B 2 times is equal to 0. So determinant A plus B is 0, that means A plus B is a singular matrix. There are other methods also you can take, but this is one of the simplest method. Using the properties of determinant we can prove this. Now I am going to take the next question. This is question number 3C. We have given a matrix A, that is 5 7 2 1 1 1 minus 8 1 2 3 5 0 3 4 minus 3 1. So this is 4 cross 4 matrix. We have to find the rank of this matrix, and we have to find the dimension of subspace V is equal to x1 x2 x3 x4 belongs to R4, and A x is equal to 0, and x values are x1 x2 x3 x4. First of all, when we write this matrix A, we will write in the proper format. That is, if I write exchange my R2, so I can write for 1 1 minus 8 1, and if I put my R3 2, R2. So this is 2, 3, 5, 0, and this R4 to R3. So this gives 3, 4, minus 3, 1. And finally R1 is transposed to R5 to R4. This gives 5, 7, 2, 1. We have to look at the matrix. Here we can see one thing, that if we add this whole row 1 and row 2, that gives me row 3. 2 plus 1, 3, 3 plus 1, 4, 5 minus 8 minus 3, 1, 1. Similarly, there is a pattern. If we add these two, we get this. 2 plus 3, 5, 3 plus 4, 7, 5 minus 3, 2, 1 plus 0, 1. Okay, so we can do matrix operation. We can write this R2 is equal to R2 minus of 2 times R1. So we can just write R1 whatever it is. Now this operation, 2 minus 2 is 0. 3 minus 2 is how much? 3 minus 2 is 1. 5 minus 16, so this gives me 21. So 0 minus 2 is minus 2. Now I am going to operate this over here. If I write R3 is equal to R3 minus of R1 plus R2, and R4 is equal to R4 minus R2 plus R3. As I have told, these two, when we are going to add, this gives me this row operation. So this whole becomes 0, 0, 0, 0, 0, 0, 0, 0. So we are only left with two independent rows, linearly independent rows. That is this row and this row. So that means the rank of the matrix is 2. So you can say that 2 linearly independent rows, hence the rank of matrix A is 2. So we have done the first part. We have to find the dimension of this subspace V. So for that we need to operate on Ax is equal to 0. So we are just going to exploit the same thing, whatever we have got over here. So I will just write over here itself, this is A and it is operated in x1, x2, x3, x4, whole is 0, 0, 0, 0. So we can write this as x1 plus x2 minus of 8x3 plus x4 is equal to 0. Similarly, we can write x2 plus 21x3 minus of 2x4 is equal to 0. Now we are seeing that we can write this x2 as minus 21x3 plus 2x4, and we can put this in this equation. So we are only seeing that there are two free variables, that is x3 and x4. That means dimension of the subspace V is equal to 2, because we are having only x3 and x4 as free variables, and we can write, after putting this one, we can write x1 is equal to minus of x2, that means 21x3 minus 2x4 minus 8 plus 8x3 minus x4. So we get x1 is equal to 29 x3 minus of 3 x4. So we get our v as x1 is 29 x3 minus x4, x2 is minus 21 x3 plus 2 x4, x3 x4, and where, and this one belongs to the power 4. So we are done with this. We have found the dimension, that is 2, and rank is also 2. Now we are going to take the last question for this session. Question number 4a. You have to state Cayley-Hamiltonian theorem and use this theorem to find a to the power 100, where a is 3 cross 3 matrix and entries are 1 0 0 1 0 1 0 1 0. Ask for 15 marks. The same question was asked in IAS 2015, where we are supposed to find a to the power 30. Alright, so this is not new, but first we have to write what is Cayley-Hamiltonian theorem. Every square matrix satisfies its own characteristic equation over a commutative ring such as real or complex fields. This is our Cayley-Hamiltonian theorem. We have to write the statement. Using this, we have to find a to the power 100. Now, this is not diagnosable, so we cannot use the other method of the power matrix. We have to exclusively use Cayley-Hamiltonian theorem. Many solutions to this question on internet, so-called reputed solutions, answer is wrong. So I think that this should be brought to your notice. So I'll write its characteristic equation. So this gives me lambda minus 1 0 0 minus 1 0 not 0 lambda minus 1 0 minus 1 lambda is equal to 0. So if I expand this determinant, this gives me lambda square minus into minus minus, and then minus into minus plus, and then minus sign, so this gives me minus. So I can write this as lambda cube minus lambda square plus 1 is equal to 0. So this is the characteristic equation as written just now, that Cayley-Hamiltonian theorem, that each square matrix satisfied characteristic equation. That means a to the power 3 minus a square minus a plus I is equal to 0. This is the statement, and this is what we have written. So that means we can write this as a cube is equal to a square plus a minus I. So if I write a to the power 4, that means I am multiplying here with a matrix. So this gives me a cube plus a square minus of a. Okay, so I can further put the value of a cube from this equation. I will write it is a square plus a minus I plus a square minus a. So this and this will get cancelled. We can write this as 2a square minus I. Similarly, we can move further. We can write this as a to the power 5. I am multiplying here with a. So that means this is a to the power 4 plus a cube. Rather, I would use this equation over here. So I will multiply here 2a to the power 3 minus of a. So I am going to use this value. This is 2a square plus 2a minus how much? 2I minus a. So this gives me 2a square plus a minus of 2i. Now I find a to the power 6. I am going to multiply over here. So this gives me 2a cube plus a square minus of 2a. So I can write this as 2a square plus 2a minus 2i plus a square minus of 2a. So this one will cancel. You can write this as 3a square minus of 2i. Our concern is a to the power 100. That means we are concerned with the even powers. Now can we find some pattern? If I write a to the power 2n is equal to n into a square minus of n minus 1 I. Here we have to be concerned about n. I am just trying to look for the pattern for 4. So if I put here n is equal to 2, that means a to the power 4 is equal to 2a square minus of I. Is that the case? Yes, here we can see this is the case. So this holds true for n is equal to 2. What about if I put n is equal to 3, a to the power 6 is equal to 3a square minus of how much? 3 minus 2. 3 minus 1, 2. So here also we are able to establish this fact. So we are just trying to generalize. Again I will find a to the power 7 and a to the power 8 to further check my values. So if I write a to the power 7, this gives me how much? 3a to the power 3 minus of 2a. So I will write these values. A to the power 7, this gives me 3. A cube was how much? A square plus a minus I minus 2a. So this gives me 3a square plus 3 minus 2. So this gives me a minus 3i. So similarly I can find a to the power 8. This is 3a 3 plus a square minus 3a. So again this gives me 3a square plus 3a minus 3i plus a square minus 3a. So this gives me 4a square minus of 3i. So if I put n is equal to 4, that means a to the power 8 is how much? This is 4a square minus 3i. So this is true for n is equal to 4 as well. Okay, so we can generalize it to the power. We could have also done by mathematical induction, and this question is also repeated in 2004, 2002 on the similar lines, but there are some constraints. So generalize a to the power 2n is obviously true, but I will put restriction on n. N is not equal to 1. If we check for n is equal to 1, this will not be true. I will just show how. So I can write a to the power 100 is equal to 58 square minus 49. This is what I wanted, but this is not true for n is equal to 1. If I take a square, this is 1, 1, 0, 0, 0, 1, 0, 1, 0. Again we will multiply 1, 1, 0, 0, 0, 1, 0, 1, 0. And now I am going to multiply this. This is 1 into 1. So this is the point 1. Similarly 1, 0, 0, 0, 0, 0, 0, 1, 0, 0. So only 1 is 0, 0, 1, 0, 0, 0. Here 0, 1, 0. Here 0, 0, 0. Here 0, 1, 0, 1, 0, so 1. So if I put here n is equal to 1, that means a square is equal to this comes something else. So a square, if I put n is equal to 1, so that means a square is equal to a square minus 0. So that comes the same. So there is nothing even crowd about this. So now I am going to use this. I can use this as a to the power 100 is equal to how much? 50 times this. So this is 50, 0, 0, 50, 50, 0, 50, 0, 50. And this gives me how much? Minus 49i. So this is 49, 0, 0, 0, 49, 0, 0, 0, 49. Now I will just write the value. A to the power 100, 50 minus 49 is 1. This is again 0, 0, 50 minus 0, 50. Okay. 50 minus 49 is 1. This is 0. 50 minus 0 is 50. 0 minus 0, and 50 minus 49 is 1. So this is the value for a to the power 100. In 2015 they have asked a to the power 30. So we could have very well written the value, that is 15a square minus 40i. So no matter whatever they are going to ask you, if you know the basic, right, and if you simply use the mathematical induction approach also, you can use it. But here it is very pertinent to understand that what is the nature of the matrix, whether it is diagnosable or not. And if they are specifically asking this to use this theorem, you have to use it, and you have to substantially prove to the examiner that whatever step you are taking, that is correct in all entirety. So there is constraint on n, and that is not true for, if I say that n is equal to 1, that will not be true. So for n greater than 3, if I take the general n greater than 3, so we can take only for these values, these induction values. We can start with odd and even, and then we can get the answer. So this is the answer to this question. You can use calculators also, scientific calculator, to find in examination to verify your answers rather than relying on fraudulent solutions on internet. Thank you for watching.